Hello, welcome to this video, and in this video we shall be looking at stationary points as an application of differentiation. Now, as curves progress, they turn. In other words, their general direction changes. You can see from the curves that we have that this leaves them with peaks. For example, the curve OAC has a peak at A, and valleys, or lowest points, highest points and lowest points. You can see this curve has highest point at A, and this curve has its lowest point at point E. Now let's look at the gradient of the tangents along the curve. Notice that if I have a tangent at point O, it will be not exactly like that. But the tangent would be something like that. If we had a tangent along there, you can see that these are positive tangents with positive gradients until point A, where the tangent at point A has a gradient of 0. And then as the curve progresses, the gradient becomes negative. Notice that for point E, it's the other way around. So we have negative gradient tangents until point E, where the gradient of the tangent is 0, and then positive gradient tangents as it progresses. And so let's look at some examples where we need to find, these turning points, because now we know that at the turning points, at the maximum or the minimum, the gradient of the tangent is 0. And so we can use differentiation to actually locate those points. So we've been asked to find the turning values of y on the graph y is equal to f of x, where f of x is this. In other words, y, we can write y as f of x, which is 5 plus 24x minus 9x squared minus 2x cubed. Now to get the turning points, we differentiate to get the gradient of the tangent. We can write dy dx like that. So this would be 24 minus 18x minus 6x squared. We could factorize this to negative 6 times x minus 1 times x plus 4, if you're keen. Now we know that the gradient of the tangent at a turning point is 0. And so for turning points or stationary points, turning points, y prime should be equal to 0. And so the x values at those turning points, we'll have 2. We'll have x being 1 and x being negative 4. Now to determine whether it's a maximum or minimum, we use the fact that for a maximum, to the immediate left of that point, the gradients of the tangents are positive, and to the immediate right, the gradients of the tangents are negative. The converse is true for a minimum point. And so we'll have a small table here to have the value of x and then the sign of the gradient function. And so we'll have x being equal to 1, and then to the immediate left of it, and then to the immediate right of it. And then we'll have another part for x being negative 4, immediate left and immediate right. They already know that when x is 1, y prime will be 0 because of what we discovered. And if you go ahead to calculate for a number, let's say 0.9, to the immediate left of x being equal to u1, you'll find that the gradient, the tangent there is positive, and to the immediate right will be negative. And if you calculated this, say for negative 4.1, you'd find that it's a negative value and this is a positive value. So what does that mean? It means that the curve progresses like this: positive gradient, 0 gradient, negative gradient, indicating that this is a maximum. And here it progresses as negative gradient, 0 gradient, and then positive, indicating that this is a minimum. And so when x is 1, you have to find the y values at those points, because the question asks for turning values of y. When x is 1, we'll substitute in the original equation, which was this one, and you find that when x is 1, your y is 18. And therefore, the point 118 is a maximum point. But the question is asked for points, that's for the values of y. And therefore, you should conclude that y is equal to 18 is a maximum turning value. And then when x is -4, if you go ahead to calculate, you find that your y is in fact -107. And therefore y is equal to -107 is a negative turning value. And that's how we compute a maximum and minimum points and distinguish between them. And so you could have a question like this, which is more subtle in that it's not exactly obvious that you have to apply differentiation and knowledge of turning point. But once you realize that you want to make something as small as possible or as large as possible, it points to the fact that we have to do just that. I've been told that 64 centimeters cubed of butter is to be made into a slab of square cross-section. So something like this. Square cross-section. And we've been asked to calculate the required length, call that the length, and the cross-section, let's call it side length x. So calculate the required length if the total surface area is to be as small as possible. Now we already know that the volume of this slab is x squared L, and this is 64 cubic centimeters. Yeah. Now we know that for surface area, I'm going to call surface area A. Surface area of that slab is going to be given by 2x squared, the two opposite faces of the square, plus 4xl, because we have 4 rectangles with dimensions x by l, so plus 4xl. This is the equation for the total surface area of the slab. Now we know from this equation right here that for this particular butter, L is given by 64 out of x squared. And we want the surface area to be as small as possible. Yeah, so that would mean we have to sort of differentiate this equation here, but it's in two variables. So we want it to be in one variable so that we can differentiate it, equate that derivative to 0, find the values of x, the value of L in this case, since it's what's required, that makes that possible. So if we substitute for L in this equation, we'll have 2x squared plus 4x times 64 out of x squared. This gives us, that 64 out of 64 times 4 is 256. This is 2x squared, is 256 out of x. Now, what do we know? We know that dA dx, the derivative of a with respect to x, is going to be 4x plus, it's going to be negative 256 out of x squared, since this is x to the power negative 1. Now we know that the derivative is 0 for minimum and maximum, area. So we will work out the value of x when dA dx is 0. So we have 4x minus 256 out of x squared and equate it to 0. If you multiply all through by x squared and then divide by 4, you end up with x cubed minus 64 being equal to 0. And solving for this tells you that your x is going to be equal to 4. And now you can confirm that x is equal to 4 will make the area minimum. How? By checking for values of dA dx to the immediate left of x equal to 4. So check for like 3.9 and then check for like 4.1. You realize that you have something like this, negative 0 and then positive. And so x is equal to 4 indeed makes the total surface area a minimum. And the value of L at that point would be 64 out of x squared in this equation, which is 64 out of 16, which is 4 centimeters. And so 4 centimeters, the answer to that question right there. Okay, So we've looked at maximum, minimum. Now we want to look at points of inflation. You realize that for some curves, like the curve that's on your screen, y is equal to x cubed, when you differentiate this, you get dy dx as 3x squared. Now 3x squared can never be negative. It can only be a 0. 0 is a smallest value that you can take on. But this can never be negative. In other words, we don't have a situation like this where you're looking at the gradient of the tangent being negative at any point. The gradient of the tangent will always be non-negative. The lowest it can be is 0. Realize that that 0 occurs at that point, and so that point is called point of inflation. And so there are some curves like this, and so it's not a maximum point, not a minimum point, but it's a point of inflation. So let's look at an example where we have a point of inflation. So we've been asked to find the turning point to this curve and state its nature. So state whether it's a maximum, a minimum, or point of inflation, like we've just seen. So given y, we can get dy dx, which is 3x squared minus 12x plus 12. And you know that this is 3 times x squared minus 4x plus squared minus 4x plus 4. So in fact, 3 into x minus 2, x minus 2 all squared. For turning points, dy dx has to be 0. And so when dy dx is 0, our x will be 2. When you solve that equation, you can calculate what the y value of is. When x is 2, y is going to be 2 cubed minus 6 times 2 squared plus 12 times 2 plus 3. What does that give? It says 8 minus 24, which is minus 16, plus 24, 8 plus 3, give us 11. Can confirm that. 8 plus 24, that's 30. 30 minus 24 is 6. 8 plus 24 is 32, sorry. So that's going to give us 11. Yeah, it is. So how do we determine the nature of this turning point? We'll draw the same table that we have. So when x is equal to 2, immediate left, immediate right, and then the sign of dy dx. Of course, we know that when x is 2, dy dx is going to be 0. When x to the immediate left of x being 2, you could go with 1.9. It's going to give you a negative, but you're going to square it. So you're going to get a positive there, and you're going to get a positive there as well. So you're looking at something like this, this, and therefore the point 2, 11 is a point of inflation, and that's how we conclude that question right there. So you realize that this table is key to determining the nature of the turning point that you're finding.